I am K. Shahul Hamid, Professor, ECE, Setu Institute of Technology. In this session, we are going to discuss linear control engineering, in particular, polar plot problem discussion. First, I will read the problem statement. Consider a unity feedback system having open loop transfer function g of s is equal to k divided by s into 1 plus 0.5s into 1 plus 4s. Sketch polar plot and determine the value of k so that gain margin is 20 dB and phase margin is 30 dB. So this is the problem statement given. In the problem, the system function, we do not know anything about the value of k. So when we really want to solve the problem, we have to assume that k is equal to 1 and solve the problem, and finally we will find the exact value of k for the given specification 1 and specification 2. So first thing is, we are going to let k is equal to 1 and then we are going to put s is equal to j omega in the system function. When we are doing that, we get g of j omega is equal to 1 divided by j omega 1 plus j 0.5 omega into 1 plus j 4 omega. Now we have to find the corner frequencies. The corner frequencies, when you are seeing the system function, we have two functions. So we have two corner frequency. One is omega c1. So first corner frequency is 1 by 4, which is equal to 0.25 radians per second, and another corner frequency is omega c2, 1 by 0.5 is equal to 2 radians per second. Now we have to find both magnitude as well as phase. Any complex number, for example, if you are taking a plus jb is a complex number, we can write this complex number in terms of magnitude as well as phase. That is, can be written in terms of magnitude as well as phase angle. For example, if you are taking a plus jb, a is real part and b is imaginary part, and we can write a plus jb in terms of magnitude, that is magnitude of a plus jb into phase angle tan inverse of imaginary part b by real part a. Now using this, we are going to write each and every term in the system function in terms of magnitude and phase. So this is system function. So starting with numerator constant 1 and denominator we have j omega. See, this can be written like omega, this magnitude of j omega is omega. Phase angle here real part is 0 and imaginary part is 90 degree. Hence phase angle is 90 degree. Now we can take 1 plus j into 0.5 omega. So here the magnitude of this one is square root of 1 plus 0.5 omega the whole square, root of 1 plus 0.5 omega square, and the third term 1 plus j omega 4 omega is written like so here actually this is a magnitude, and phase angle of this one is tan inverse of 0.5 omega, that is 0.5 omega is the imaginary part, real part is 1. Next term is 1 plus j 4 omega, and the magnitude of this number, this complex number, is square root of 1 plus 4 omega square, and phase angle is tan inverse of 4 omega. Now I am going to separate this terms like imaginary part and separate magnitude and phase angle. So I am going to take the magnitude 1 omega, that is this one and this one. So I am going to write the magnitude is separately, and the phase angle I have 90 degree, then tan inverse of 0.5 omega, tan inverse of 4 omega. So when we are comparing these things, so we have to add this phase angle, then the final is 90 degree plus tan inverse of 0.5 omega plus tan inverse of 4 omega. Now this phase angle is in denominator. When we are moving to numerator, plus simple become minus. So this I am rewriting like minus 90 minus tan inverse of 0.5 omega minus tan inverse of 4 omega. So this is the final one. So we started with the system function. It's a complex number. Then we have separated magnitude and phase, and now we have written in terms of magnitude as well as phase. This is magnitude, and the second one is phase angle. Now we have to substitute different values to this omega, and we have to find magnitude as well as phase angle. So first starting with, and this range of frequency should be we have to derive from corner frequencies. We have two corner frequencies. One is 0.25 radians and another one is 2 radians. So we have to consider these two, and finally we have taken the range from 0.3, 0.4 and it go up to 1.2 in order to plot the graph. So for 0.3 the magnitude is around 2.11, the phase angle is minus 149, 0.4 1.3 and minus 159. For 0.3 radians per second, magnitude is 0.87 and phase angle is 167 and so on, and we are going to plot in polar graph. This is polar graph, and in polar graph when you are seeing this they have given phase angle as well as magnitude and outer part. So these are actually phase angle, and the circles which you are seeing, these are all actually called magnitude, and it depends upon the range of value. When you are seeing magnitude range, it's starting from 0.15 and the highest value is 2.11. And when you are seeing phase angle there is no problem because already it is listed. When you are seeing this, so anti-clockwise the we have to take positive values, this 10, 20, 30, 40 and so on. When you are taking clockwise, we have to consider negative phase angle, that is minus 10, minus 20, minus 30 and so on. So you can see both positive and negative, clockwise and anti-clockwise. Now depends upon the magnitude range. So we have to choose the circle here. One circle is 0.04 magnitude. So it means not for the sense this is first circle, this is 0.4 and 0.8, 1.2 and 0.8, then 0.8, then 0 plus 0, 1.2, then 1.6, 2, so on, it will go like that. Now we have to take both magnitude as well as phase angle. We are considering the first one 2.11, the corresponding phase angle is 149. 149 is, so this is minus 30, and when you come here this is 140, and 150 minus 150 is here, and 149 it's very close to 150, and we have to see 2.11. So one circle the diamond, I mean the magnitude is 0.04. So we have to take 2 is here, this is 2 circle, and 2.11 is around this is 2.04, 2.08, and this is around here. So this is 149, 2.11. So minus 149, 2.111. So this is the first point. Second point is 1.3. 1.2 is here. 1.3 will be something around the second line here, and here phase angle is 159. 159 is very close to here, minus 160. So this point is second one. Third one is 0.87. It's close, it's after 0.8, and it's around here 0.8, and it is 7 0.8. One circle is 0.04, so this is 8, this one is 0.84 and 0.88. It's something around here, and the phase angle is minus 167 in between 160 and minus 170. It's something around, so they have drawn the dotted line represent that one. So the exact one is something 167. It's something here, around here. So this point is minus 167, 0.87, and the next one is 0.61. 61 is in between 0.4 and 0.8, so it's somewhere here, and the phase angle is 174. 174 is above minus 170, and it's okay, it's around here. So this point is the next one, and 0.35 minus 184. 184 is above minus 180, so it's somewhere here. So 35, and at this point, this points. After marking all these points, we have to connect all the points freehand, and it should be joined with the origin. So this is the origin. So we have plotted polar plot, that is magnitude versus phase angle plot we have completed. Now we have to find out gain margin and phase margin. So gain margin K suffix G is equal to reciprocal of gain at phase crossover frequency, that is G of J omega P suffix C. So gain crossover frequency is nothing but the locus of the plot, okay, locus of the plot which will cross minus 180 degree line, so this line. So we have to find the value of the magnitude at the where the locus is cut the minus 180 degree line. So this point here, this is 0.4, and each circle is 0.04, so this point is 0.44. So now we have to take the reciprocal of this point, that is 1 divided by 0.44 is equal to 2.27, and here we assumed that K is equal to 1. At the same time, phase margin gamma is equal to 180 degree plus pi GC. Pi GC is nothing but phase angle at gain crossover frequency. Gain crossover is nothing but the locus of the plot will cut the magnitude of radius 1, this point, that is this magnitude of radius 1 unit circle, this point, and we have to measure the phase angle. So you just connect this point and the center point and extend in this, you will get a phase angle. This is somewhere in between minus 160 degree and minus 170 degree. It's around 165 middle, so 165. So 180 degree minus 160, it is around 15 degrees. So we have determined gain margin and phase margin for K is equal to 1, that is by assuming K is equal to 1. But in the question they have given data like gain margin should be is equal to 20 dB, but we have assumed that K is equal to 1, and we have determined the gain of gain in dB, that is when K is equal to 1, kg already we have determined kg is equal to 1 by 0.44, which is equal to 2.27, and gain margin in dB is equal to 20 log 2.27, which is equal to 7.12 dB. Now here the actual gain should be 20 dB, but we have only 7.1 dB. It has to be increased to 20 dB. 7.12 dB must be increased to 20 dB. Hence K has to be decreased, the gain has to be decreased. So we have to let G suffix A be the gain at 180 degree minus 180 degree line for gain margin is 20 dB. Then 20 log 1 by GA is equal to 20. So log 1 by GA is equal to this 20 will come here. So 20 by 20 is equal to 1. And when you are taking antilog both side, 1 by GA is equal to 10 power 1 and GA is equal to reciprocal 1 by 10 which is equal to 0.1. So the value of K given by K is equal to GA by GB which is equal to 0.1 divided by 0.4. We have to find the ratio of new gain and the gain at K is equal to 1. 0.1 divided by 0.44 which is equal to 0.22. This is the new gain, that is for gain margin 20 dB. So gain margin 20 dB, the new gain is 0.227. Similarly, when K is equal to 1, we have determined phase margin is 15. But in the second case, we have to find gain for phase margin 30 degree. So it has to be that 15 degree phase margin has to be increased to 30 degree. So if you really want to increase phase margin, then the gain has to be decreased. So we must know the formula to find out gain margin. Gain margin gamma is equal to 180 degree plus pi GC by GC. So gain phase angle at gain crossover frequency. Now we have to, already we have determined that gain margin is 15 and the crossover frequency is around 165 degree minus 165 degree, that is G pi GC1 is 165 degree from the figure. Now we are going to let pi GC2 is the phase crossover phase angle of gain crossover frequency 2, and we are going to modify it. So first gamma is equal to this formula 180 degree plus by GC2, and pi GC2 is equal to minus 180 degree plus gamma, and the new gain is 30 degree. So substitute is phase margin is 30 degree. So minus 180 degree plus 30 degree which is equal to 150. So actually in this 1 degree line the locus should cut and we have to find the magnitude. So I am going back to the graph. Here this is the locus. So locus, we have to draw a line from minus 150 degree to the center point, and this particular line will cut the locus, okay, and we have to find the magnitude. This is 2, and the next line is 2.04. So this is the new gain for new gain crossover frequency 150 degree. Initially we have assumed that this is the gain crossover frequency, that is the locus cut the unit circle, and we are considering this is point D, and the new one is C. Okay, here this is 1, the magnitude is 1, and the new magnitude is 2.04. So we have to so already we know that GC is equal to 2.04 and GD is 1. We have to find the ratio. K is equal to GD by GC, which is equal to 1 by 2.04 is equal to 0.49 is the new gain. So according to the given specification, for 20 dB gain margin, the gain K is equal to 0.227, and for phase margin 30 degree, the new gain is 0.49. So we started with the problem, and we have modified the phase margin and gain margin, and we have found the new gain for both gain margin as well as phase margin. So this is the end of the problem. Thank you very much. Thank you.